Pogaku Garu, and Director Dr. C.V. Krishna Reddy Garu, NNRG, Dean Dr. G. Janardhan Raju, all Deans and all HODs, and HOD of EEE Department, Dr. P. Ramesh Garu, and all the participants from various organizations. Now I request Dr. P. Ramesh Garu, HOD of EEE NNRG, to welcome all the participants.
Respected today's speaker, Dr. Nagaraju Pogaku, and Director and Dean School of Engineering and various schools of NNRG, all head of the department, and all the participants from various institutions. Good morning to one and all. First of all, I would like to welcome you to the national webinar on grid connection of renewable energy generation, challenges and solutions. Yeah, nowadays, presently, you know the value of energy. Generally, we can say that every nation can be depends upon the major 4 dimensions. The first one is energy. Second one is infrastructure, information technology, and biotechnology. In the scenario of the global problem happening, the situation of COVID-19, you know that every time we are saying about the nation development, this is the time to secure the nation also. We can secure through the health and the people by means of utilizing the many technologies. Now we are rapidly increasing the technological policies as well as a requirement of the tools development of the health. Remaining all the aspects, you need to synchronizing with the and also utilizing with the majorly digitalization. Increasing the digitalization of utility, definitely we can say that we require the power. Here we are facing the major problems and challenges, the sources of energy generation. We are increasing the demand with respect of the aspects of all the technologies. Definitely we can balance the generation as well as the load, so that the means of integration of this part of renewable energy or some conventional energy, all the things, definitely we majorly can face some challenges and problems. How can you balancing the both demand as well as the generation by means of adapting the some technologies? Really, what are the problems we are facing in the means of integration part of the energy and as well as the demand? So that in the way, definitely we have to know about really what problems we are facing, what are the solutions happening to give the reliability supply and also the success grid integration between the generation as well as system. Definitely, really this is a permissible research area. Definitely this area is very important as well as a prominent present days, so that everyone should have some idea about being a power engineer, idea about grid interconnection of some sources is very important. In that connection, we have chosen the best speaker or suitable speaker for this webinar. I hope this webinar is very benefit and as well as useful for all the participants who are seeking the really the research on the way of power system. Thank you, sir, for your acceptance when we did propose about our webinar he immediately invited and also he accepted our proposal. Thank you very much for your cooperation for us to organizing this webinar. Dr. Nagaraj Garu.
Thank you,
Thank you,
sir.
sir. Wish all the best to all the participants. Thank you.
It's my pleasure.
Thank you, sir. Thank you for your valuable words. Now it's privilege and honor to introduce today's speaker, Dr. Nagaraju Pogaku Garu. Dr. Nagaraju Pogaku received the BE degree in electrical and electronics engineering from Osmania University, Hyderabad in 2000. The MTech degree in electrical engineering with a specialization in power electronics and power systems from IIT Bombay, India 2003. And the PhD degree from Imperial College of London, UK. He is currently working as a senior consultant ENO London. His research areas includes the distributed generation, microgrid, applications of power electronics to power systems, and deregulation. A chartered electrical engineer, IETE specialized in electrical power system research and analysis. The academic highlights of today's speaker are authored one of the most cited general papers in the field of microgrids, a regular reviewer of IET, IEEE general papers, received Overseas Research Students Award Scholarship for PhD students for PhD studies from the Secretary of State for the Education and Science, UK. So thank you, sir. We are very much pleasure to have you for this webinar. Thank you for accepting our invitation and giving a webinar on grid connection of renewable energy sources, challenges and their solutions. Thank you, sir. Now I request our speaker to hand over the session.
Great. No, thank you very much for very kind words. So good morning, all.
Good morning,
I hope you're all keeping safe in this pandemic, and thank you for joining this session despite all the difficulties. Many people may not have good access to internet and maybe staying at remote locations with families and everything. So I appreciate for joining this, and thank you for giving me the opportunity to speak you all. So just let me again introduce myself. I'm Nagaraju Pogaku. My background is mainly in innovation aspect of power systems, renewable energy, microgrids, smart grids, and power electronics. So I have been a pure power electronics engineer for a long time, but lately mostly has been a kind of R&D type manager in my company. So I'm a principal consultant with a London-based company, and I'm responsible for grid connection issues of renewable generation, as well as power-related innovation aspects for the company in UK. Okay, so I think Dr. Ramesh has already given you very good introduction regarding the challenges about variable generation sources, their importance of integrating into the grid, and the importance of actually the energy dimension, energy security and everything. But one aspect that I want to remind you is when we talk about renewables, we are mainly talking about the climate, which is perhaps the utmost, at least for personally, it should be the utmost importance for any human being on this earth. Renewable energy has been there for decades, and it's going to be, there's the only future going forward.
Excuse me, sir.
Yes.
Sir, can you be a bit louder, sir? All participants are asking that.
All right. Okay. Any better? Can you hear me? Any better?
Yeah. Yes, sir.
Okay. So I was just trying to put the context for this presentation. Now, why do we need to, learn or study about renewable energy and the integration of renewable energy into the power grids? So what I did in my presentation, I don't know, I'm not an academic speaker, So I work in industry. So I try to the industry side flavor to you. I'm sure you are much better in terms of academic challenges. I'm seeing the fundamental challenges, whereas I'm coming from the industry side. Although I have a lot of academic background in, so I'll try to give you a flavor of industry, what the industry is seeing some issues in terms of integration of the renewable energy into the grid. So I prepared this session as a kind of a question and answer session rather than a stereotypic academic lecture. I divided this lecture into 4 parts. One is, first question is, what is the relevance of this renewable energy now? And why do we need to be concerned? How big it is? Is it there already? And what is going to happen in the future? So we will look at the fundamentals of renewable energy. Then we will move on to the technicalities of renewable energy. Now, why what are the differences between the conventional generation and the renewable energy generation sources? There is a bit of disclaimer I want to give you on 2 things. One is, I'm not going to cover the challenges of every possible or potential renewable energy source, but I will be mainly concentrating on 2 important renewable energy sources, wind and solar. Other technologies, some of them are matured, but not acceptable due to various limitations like environmental footprint or cost, etc. And some of them are immature at the moment. They are still in R&D phase. But wind and solar, we know everyone, I mean, it's already there and it's huge. I mean, I will explain you with some big numbers around the world what we are looking at. So in terms of technicalities, yes, so we will look at the actual technical differences. Apologies to everyone. I mean, if it is too technical at some point, I don't know the depth of the people here. I don't know how, I mean, whether it's purely electrical related lecturers, professors here, or some generic people as well. But after midway through my presentation, I will move on to some fundamental technical issues. I hope it's not an issue for you. Then after explaining the technical differences, I will come to the important aspect is challenges. Yes, we know that these technical differences are there. Then what are the challenges to the grid? Why the conventional grids are concerned with these non-conventional generation resources? What is making them worried? And what are the grid codes are asking for? You know, when the grid operators are trying to operate the grid safely and securely, what are they looking for and what are they asking this renewable energy generation to come up with? Then finally, I move on to the solutions to overcome these challenges. And I will give you some real examples, real example in the sense that the projects I worked in the last few years, how I approach and how I propose solutions. Now, one aspect you may be asking, what is the research matter in this? I will touch upon those as well. Most of the presentation would be pure technical aspects. So there will be scope to discuss through some of the research opportunities. Okay. Right. So renewable energy generation, what are they? I mean, this is a bit of a boring slide, I know. You know, everyone knows what is renewable energy. So as I said earlier, 2 prominent renewable energy sources that we will talk through, wind and solar. Hydro, yes, has been there for decades. Well, some people say it's conventional, some people say it's renewable. But for me, it's both. It's well established and perhaps the first energy source to be converted into electricity. So I'm not going to talk any details of hydro energy related aspects. And other renewable energy sources, let us see biomass. It's a well-established technology. And some of the Western countries and even in India have a lot of biomass plants. But again, given that environmental footprint is huge and the resource is limited, I'm not seeing much future for biomass. Yes, it will be there, but not as big as any wind or solar. Tidal, there are still conceptual level of projects, research projects happening around the world. I was involved in one project about 8 years ago. Palamis wave, actually, not tidal. But given the huge technical challenges, they are still not matured to be commercial. Same applies to geothermal. So I'm not going to touch these technologies. I will touch upon wind and solar, and we will see why they are important, why we are talking only those two. Now, how relevant is renewable energy? Okay, what I'm doing here is on the left-hand side, you will see on the slide in the green bit, I will try to ask the question, and on the right-hand side, I will try to give you the context. Just let me know this. So let's look at the wind first. Starting about 1 kilowatt range in 19th century, now we are looking at almost 15 megawatt capacity for one wind turbine. Where are we now? Last year, General Electric has come up with the 12 megawatt turbine with a hub height of 250 meters, almost approaching the height of Eiffel Tower. And these are monsters. These are huge. So why am I giving this context here? Because I'm trying to give you or explain you that renewable energy sources are big already. How big are they? Sorry, good morning. How big are they? Let's look at some of the wind farms around the world. I mean, China both saying that 20 gigawatt in the Jiquan wind base, but these are multiple plants in the same geographical area with the different grid connections. So I wouldn't consider them as a single wind farm as such, but within one geographical area, they have concentrated nearly 20 gigawatts, and it's all connected through HVDC to the mainland. In India, we do have very big plants. Mupandal 1.5 gigawatt, Jaisalmer 1 gigawatt. And the technology now has already moved to offshore. I mean, offshore, there is a lot of space. There is a lot of wind. And one project I worked on is Hornsea Offshore, UK. It's 1.2 gigawatts. It just came to operation now. And in 2009, I think I did the grid connection application for that plant. So the renewable energy plant sizes or farm sizes have already reached the conventional generation and probably are already exceeding the conventional generation sizes. Solar, they are not far behind. Some of the largest solar farms are already in India. Given the abundance of solar radiance in our country, I mean, we see the solar as the future compared to wind. I mean, if you look at West, although this list does not boast much about the UK or United States less much, but the overall capacity wise, wind is far ahead than solar, whereas for us in the south and southwest, it is the solar that is going to be the future until the offshore wind takes over. So we have, for example, in Andhra Pradesh, 1000 megawatt wind park near Pavagada, which I think visited a couple of years ago. So already solar plants as well have exceeded 1 gigawatt capacities, and they are coming up in huge numbers. So that is the relevance of renewable energy in terms of their capacities coming up. Now I want to give you some flavor of what is the market for the renewable energy already in some of advanced countries. So another disclaimer I want to give you is that in the past 15 years of industry experience, I have always worked in Europe and some of the Central Asian countries. So to be honest, I don't have much experience in Indian context, but I know some of the background information. So I will try to elevate you that. Now, so look at Germany. So just let me take a pen. So this picture shows, sorry. The Germany picture last year in 2019, in terms of energy produced, electrical energy produced by various resources. And you see that renewable energy is already doing 40% in last year. That's huge. We are not talking about 10%, 15% where grids can easily accommodate, but we are talking about 40, 50%. This picture shows the right-hand one, the UK energy mixture on 30th June 2019. On that day, more than 50% of the energy was coming from renewables. And the bottom picture shows the renewable energy penetration levels in Europe. And you will see that a lot of countries have already approaching either 50% or exceeded 50% penetration levels. So these are huge numbers. So grids cannot ignore these anymore. Now what's happening in India? The left side picture shows in the middle of last year, the energy, capacity, installed capacity mix. And you see that 35% of the capacity is already renewable energy. And of course, it includes a large hydro, which is about 12%. But even then, we are talking about nearly 25% of capacity is already renewable energy. And in terms of gigawatts on the right side, yes.
Can you zoom your PPT screen, sir?
Zoom?
Screen.
You want me to zoom the screen?
Yes, sir.
Okay, in that case, I just need to escape.
All participants are asking that, sir.
Sure. Just, are you still able to see my screen?
Yeah, of course. Yeah.
So this is the picture at the end of last year or beginning of this year in terms of installed capacity. You see that 86 gigawatts out of 370 gigawatts is renewables. That's excluding hydro. So wind is already 37 gigawatts, solar 31 gigawatts, and other is small hydro and bio. So this is about 25% already within the mix. I'm just shifting to presentation mode. And what is the target in India? In 3 years' time, we need to have 175 gigawatts of renewable energy. So we are halfway through, I mean, around 50% reached. And out of that, we need 100 gigawatts of solar, 60 gigawatts of wind, and rest is from biomass and small hydro plants. So the targets are huge. And we are already reaching the kind of levels of 25, 30%. And recently, before Corona, I would say, I mean, our life actually turns to be like, before Christ, after Christ. Now it will be before Corona and after Corona, I guess. So before Christ, Indian government started talking about 450 gigawatts of renewable energy by 2030, which looked plausible. And even 175 gigawatts in 3 years looked plausible, but I don't know where we will end up after the Corona situation, whether the government will have enough funds to support this. I mean, renewable energy requires a lot of subsidies. It's not that they have not yet reached the levels of a market where we can not provide any subsidy any further. One or other form of subsidy is still required. It is political to debate. I can debate with you whether it's still required or not, but there are some morphed costs that were subsidized for renewable energy. So going forward, we don't know whether we will reach the targets after Corona. Okay, so that is the context. So the thing I wanted to say is that renewable energy is huge, is already there, and is going to be everything in the future. Now, the technicalities of renewable energy. So what the thing I want to convey here basically is that what are the technical differences in terms of interfacing to the grid that would make the renewable energy challenging to the grid. I'm not going to cover every bit of technical aspects around the generation, but as I said, the topic is connection to the grid. So I will stick to that point and I will give you the important technical differences that are making this renewable energy challenging. Okay, so let's look at the wind. We started with fixed speed machines long time ago, which are not controllable and requires a lot of reactive power compensation. And they are now more or less obsolete. So nobody is making them, to be honest. Then we moved on to variable speed machines. And out of that, we started with the doubly-fed induction generators. Are you able to see my screen or do you want me to zoom in again? Any?
Yes, sir, we can able to see, sir.
All right, okay. So doubly-fed machines, they are interfaced directly to the grid, but the rotor is kind of decoupled. The rotor excitation is through a converter, which takes the energy again from grid and feeds to the rotor. So in a strict sense, the rotor is disconnected to the grid, with the grid, whereas stator is actually connected to the grid, and that makes or poses a lot of challenges. Then we moved on to the full converter technology, where the full energy source is interfaced to the grid through this power electronic converter. So the converter is acting as a transmitter of the energy from the source to the grid. This is the grid, and this is the source. So, I mean, even the defects are slowly, I think, fading away because of the challenges, because the doubly-fed machines cannot be fully controlled. So through the rotor excitation, you can control around up to 30% levels in terms of speed. So they are slowly going back in the stack, whereas the full converter wind turbines are now taking over the market. So they are now prominent. So what is that? That is major difference with the conventional generation. That is the power electronics. The power electronics are acting as a energy transmitter between the source and the grid. That's what is the major difference. Now, if you look at the wind farm layout, what we have is usually these are made up of multiple strings with individual wind turbines interfaced through their own step-up transformer. And these strings are usually rated around, usually around 33 kV string voltage. And there will be a step-up transformer at the grid connection point connecting to higher voltage. Now, what is the importance of this? So large wind farms typically made up of a number of turbines spread over a large geographical area. They involve long cables and a number of wind turbine transformers. So what are they making? Or, they are just, all these are adding up to the reactive power compensation requirements. They themselves are reactive elements, but they are challenging because it's a mix. There are cables and there are transformers. When we talk about inductive side reactive power, the transformers become challenging. And when we talk about capacitive side reactive power, the cables become challenging to compensate for. So we will look at that when I come to the practical applications. Solar, again, same story. So the power electronic converters are acting as a medium between the source and the grid to transmit the energy produced in the PV arrays as a DC to AC side grid. Then again, similar story here. The wind farm, the solar farms have large geographical areas with the cables and transformers, PV transformers. So they all add up to the reactive power requirements. Okay. Then, those are basically the fundamental differences. Now, what are these fundamental differences making them different to the conventional generation? So on the top slide, I'm showing you the thermal power station connection. Well, they're basically various components. And here, the generator is connected directly to the grid on the AC side. Whereas the wind turbines and solar farms, sorry, I'm just reiterating the same story, but it's important to understand why this becoming a challenge. So these power electronic converters are decoupling the source or turbines or PV farms from the grid. So they're not synchronous anymore. Whereas previously synchronous generators are directly connected to the grid and they are forming the frequency, they are forming the voltage, and they are helping the grid to maintain the frequency, maintain the voltage through excitation systems by providing reactive power. But here in the renewable energy sources, the power electronic converters are decoupling the source side, so making the grid's lives a bit difficult, challenging. I'm not against power electronics. Actually, I work in power electronics industry. I'm not against power electronics, but I just want to show you what is the challenge here, which element in the systems are making the things difficult. But we will see in a few slides later, that these same power electronic systems can actually act as a solution. So they pose the problem, but they can also act as a solution. So we will see that. Then other challenge we have, or other difference we have, I'm not going to challenges yet, grid challenges, but in terms of differences to the conventional plants. So the conventional plants thermal plants, gas, nuclear, they're all base load plants, and they can be controlled both for base load for the coal and the nuclear, and the gas plants for fine tuning in terms of real-time demand matching. But the renewable energy, the intermittency is the biggest issue, because the source is not in our hand. It is the nature, and it changes abruptly over the time. So let us say a solar farm spread over acres of land. On one end we can have a cloud, and other end we may have full sun. So these all dynamics act and make the output as highly variable source. The picture on the right hand side here, I'm showing you. You don't have to see in zoomed version, because you can clearly make out that the power is fluctuating. So this is the German energy output from renewable energy sources in 2012. I mean, even in 2012, Germany already had huge amounts of renewable energy. And the axis, remember to look at the axis, we are talking about terawatt hours here, not any megawatt hour, gigawatts. We're talking terawatt hours. So the fluctuation is huge. You will see that within a day, the fluctuations are huge. Here, the orange one shows the solar output in the country, and the green one shows the wind. So intermittency is an issue and poses challenges in terms of dispatching this energy, as well as in the real-time control. Okay, so those were the technicalities of the renewable energy that I wanted to talk. I mean, there are many other minor issues, differences. I'm not going to cover everything given the time. So we will concentrate around the challenges that are the result of these technical differences with the conventional generation. All right, so in terms of challenges, I have divided the renewable energy challenges to the grid into 4 parts based on the fundamental parameters of the power grids, as well as the operational issues. The fundamental parameters of any power grid is frequency and voltage. And there are operational issues as well in terms of actual power quality, because the grid operator is responsible to provide a standard quality power so that the grid consumers do not complain. And there are other planning issues we will touch upon. So let's go one by one. Frequency. So as I said, in the conventional systems, synchronous machines have been the backbone to the grid in terms of controlling the frequency. So what are the different parts of frequency that the grid will be, that we can actually distinguish? One is the inertia. So that the inertia is the kinetic energy within the grid that acts immediately after a disturbance. And this kinetic energy is coming from the rotating mass of the conventional generators, the rotors. Now, with renewable energy, as I said, the source side is kind of getting disconnected or decoupled from the grid. We are losing that inertial response. In the next slide, I will show you with an equation what is the theoretical background for this. But this is general sense. I mean, any large mass would instantly try to object any change quickly. So in here, for the grid, it is the frequency change that would be stopped by rotating mass. But as we as the conventional power plants being replaced with renewable energy, we are losing that inertia capability. Second item is the frequency following capability. So you probably know better than me, the primary and secondary frequency response that is required to bring the frequency back into the statutory limits. The renewable energy sources do have some capability to support that, but not as high as the synchronous machines based conventional generations. Similarly, demand following, due to the lack of control over the source, it is difficult to dispatch them and make them demand following source. Then the next important bit is the voltage. So as we know, the voltage has to be maintained within certain limits, otherwise the grid will collapse. So grid is all the time seeking for the reactive power support to maintain this voltage. From our basic studies of power systems, power flows equations, we know that voltage and reactive power are interdependent. You can control the voltage through reactive power. You can control the reactive power by making a voltage difference. So they are purely interdependent. So again, the conventional systems, the synchronous machines have been providing the reactive power support, and they have been the backbone through their excitation systems and AVRs. But we don't have that facility in the renewable energy context. We do have the inverters, the converters, which do have some capabilities. So we will talk about that as well. So I'm trying to give you the flavor of challenges here. So then we move on to the system planning aspects. So dispatching is an issue. Long-term dispatching, day-ahead dispatching, even day-ahead dispatching is difficult with renewable energy. Although now the markets have matured a lot in terms of forecasting algorithms using artificial intelligence and all that, but still real-time matching of demand with renewable energy source output is challenging. Another aspect in terms of operational requirement is the fault ride-through. So when there is a fault on the grid, voltage dips. And previously, the conventional machines have been able to ride through that and keep connected to the grid without tripping. What happens if during a fault, if generators keep on tripping under low voltage, you will lose further generation and the voltage will dip further, and we may end up losing the grid entirely. But the conventional generators have been helping us to maintain that. This is not the same with renewable energy. We will see that. The other aspect is power quality. So we talked about converters interfacing the renewable energy. So harmonics, flicker, and corresponding voltage dips, etc. We do have issues. So I worked on quite a few of these projects. So I can give you some practical examples on this. Okay, given the time, okay, this do have right. Okay, let us tackle one by one. The frequency. This is a well-known picture. I'm sure you must have seen this. So this shows the grid frequency variation upon loss of a generation. So here, a sudden loss of a conventional machine would lead to an abrupt fall in inertia. And then how quickly it can come up and to what level interfaces, or making the renewable energy sources to not help the grid. So because the source is decoupled, we have almost zero inertia response for some type of renewable energy which are prominent, like PV, right? And in terms of primary and secondary response, the renewable energy sources do have some limited capabilities, and they do help, but not to the same level as renewable conventional machines. Okay, as I said, I'm just trying to give you a theoretical explanation. So inertia indicates the amount of kinetic energy stored in the system. So previously it is basically the rotating mass of the conventional machines. Now with renewables, we are not having that, although wind turbines do have, they do, but they are disconnected or decoupled from the grid. We cannot count that. So in terms of fundamental equation, you see this equation here, it shows the rate of change of frequency as a function of various parameters. And one important parameter is the time constant h, which is the inertia constant. The more the inertia constant, the less the frequency change. That is the inertial response. So what are the inertia constants of various machines? So synchronous machines, we usually say 3 to 5 seconds. And asynchronous machines like induction motors, we have 4 to 5 seconds. Then doubly fed machines, which are induction generators, again 4 to 5. But as I said, the definition of time constant here is not strictly applicable because the rotor is kind of disconnected from the AC system, right? Then the full converter interface to renewable energy, which has a front-end power converter, has zero inertia. So as the large conventional generation plants are being replaced with renewable energy plants, the grids are losing the system energy. Just to give you an example, August last year, there was a huge outage in UK around London. Nearly 3 million people lost the power. And what the reason was the system inertia. The system was, it was a sunny day, mostly renewable energy was there. And conventional, only 4 conventional plants were running. And there was a fault on a transmission line, led to tripping of a nearby conventional plant, both renewable as well as, actually first renewable started falling off because on the rate of change of frequency, and followed by the generation, conventional generation. So frequency was falling abruptly. Then active power control. So we just talked about the inertia part, then active power control. So on the left-hand side, I'm showing you the grid code. So you look at that on the green part, again, I'm asking you a different aspect here is the grid code requirement. So what are the grids are looking for? So left side picture is Indian grid code. And you see that the Indian grid code requires the renewable generation to provide constant output across a frequency range of 47.5 to 50.3 Hertz. And output should not fall below 50% for the frequency up to 51.5 Hertz. For conventional plants, it's easy, but for renewables, it's challenging. Whereas on the right-hand side, Great Britain grid code. Just a disclaimer, as I said, I've been mostly working in the European side projects all these years. So I will try to give you as much information as possible regarding what is happening in those advanced markets. So again, here you can see that the output can change around 5% across a frequency range of 47 to 49. Then above 49 to 50.5, the output has to be constant. Okay, so then that is the requirement from the grid codes. So then next challenge we talked about was the reactive power. So again, I'm trying to show you some of the fundamental equations, reactive power and voltage interdependencies. So adequate reactive power is needed to maintain the grid voltage. And traditionally, synchronous machines have been providing that. And lately, in the last few decades, the flexible AC transmission devices such as SVC and STATCOM have been helping the grids to provide that. But the converter interface machines do have some limited capabilities. Manufacturers are now coming up. You can see the bottom picture shows the reactive power capabilities of a 2.5 megawatt PV inverter. So what here we are seeing here is the x-axis is the active power, y-axis is the reactive power. So when the machine is running at full rated active power, we will not get any reactive power. Reactive power is 0. And whereas a lot of grid codes do actually ask for some reactive power output when the machine is running at its rated power. When the machines are running at less active power output, they can provide a lot of reactive power support, but grid requirements are challenging here. So what are the grid codes are asking? So the first picture on the left side is Indian grid code. You can see the y-axis is the voltage and x-axis is the reactive power in terms of power factor, lagging or leading. Okay, so Indian grid code asks for reactive power support between 0.95 lagging to 0.95 leading across voltage all the way from 360 kV to 425 kV if the connection is at 400 kV level, and similarly for other voltages. So the machine has to stay within these boundaries. Similarly for the Great Britain, again the reactive power requirement is between 0.95 to 0.95 lag to lead, and again the machine has to stay within those boundaries. And other dimension is it also explains what is the amount of reactive power as a percentage of real power as well. So that is the reactive power related challenge. So here I'm only talking about the static reactive power capability, but when it comes to the dynamic reactive power, the generators have to have reactive power support and in this entire range as a function of time as well. So when the grid asks to provide reactive power, from the time it gives a signal to a generator, the reactive power support should be available within 1 second, at least as far as I know in UK. Within 1 second, the turbine or solar farm has to move from fully lagging, leading to fully lagging and vice versa. So that kind of dynamic response is also required, not just the static requirement. That's what makes them challenging. So another aspect we looked at is the low voltage fault ride through. So I think I explained this already. So conventional machines have been helping the grids to ride through the faults by not getting disconnected. And traditionally, the small distributed generators have been allowed to get disconnected when there is a fault or when the voltage is pretty low. So usually rock-off relays are set on the distributed generators. So when the rate of change of frequency goes above certain value, then they get tripped. But that's not going to be the case in the future. It's already not the case in UK. Even these distributed generators have to be connected during the faults. So what is the issue with the renewable energy sources that are interfaced by power electronics is that power electronics machines get disconnected themselves when the voltage falls below a certain value. Grids don't want to happen that. That is the challenge. The tripping is inherent design within the inverters previously because of the component tolerance levels. But now the manufacturers are coming up with innovative solutions to tackle this issue so that they don't get disconnected. They use a lot of techniques like such as crowbar systems, diverting the rotor currents, all those techniques to go through this. So what are the grids are asking across the world? Again, I don't know, it's too much information. Let us firstly stick to the Indian grid code here. So what is the grid is asking is that, so on the x-axis we have time and the y-axis is the voltage. If at the point of connection where we are connecting the renewable energy, the voltage is above this solid line, the machine has to be still running, operational, should not get disconnected. Below this, it can disconnect. So in India, as per Indian grid code, for if it is a 400 kV system, the voltage can go as low as 60 kV at the connection point. And if it is a wind turbine, the wind turbine should still continue to be operated and providing the reactive current to support the voltage. So entire region must not trip. You can see here, must not trip. And below this solid line, it can trip. Similar philosophy across other countries, Great Britain, Australia, and this picture, the middle picture shows for some other countries. So that is the fault ride through requirement by the grids. Then power quality issues. I'm not touching on the voltage dip or flicker because there's a bit of too much technical detail. But one thing that people are very much aware is the harmonics. So the power electronic converters do produce harmonics. They inject harmonic currents, and the renewable energy interfaced power electronics that are interfacing renewable energy are no exception. So they do produce harmonics. And the grid operators have a set of planning limits. They are very much, a lot of them are country specific, but mostly derived from international standards such as IEEE 519 or IEC 61000. So we all know IEEE is mostly towards the in America as well as in India, we follow here, whereas IEC is mostly Europe centric. So what is the requirement here? Just maybe let me zoom in a bit once. I don't know how well you can see. Quickly, I will zoom in and show you. So in terms of harmonic requirement, so as per the new standard 2014 IEEE 519, if the connection voltage is 161 kV or below up to 69, you can have 2.5% THD in the grid voltage. Now, when you go to the grid operator and say that I'm going to connect a 100 megawatt wind turbine, wind farm, then he will ask you what is the harmonic injection into the grid. Then if it comes out that this wind farm is causing the THD to go beyond this 2.5 THD, and then they are eligible to reject the connection until the developer goes back and comes up with a solution to fix that. Requirements, mostly centric around IEEE. So, okay. So solutions at a glance. Again, I have 4 parts: frequency, voltage, then operational issues such as fault ride through, and the power quality. So frequency, as the issue is the source side in a power injection into the grid, some of the latest or state-of-the-art solution is to use energy storage systems to support the renewable energy to provide the required frequency support. Now I will show you the energy storage solution is actually coming up quite heavily, and I worked on recently as well. So that is seen as one of the major solution to solve this problem. Again, energy storage systems that are kind of fast acting ones, not the kind of thermal energy storage or hydro energy storage, not those systems I'm talking about, such as battery energy storage, which is again interfaced with the power electronic systems. So as I said, same power electronic systems are the solutions to the problems that they have created. So energy storage, one solution. Then we have a demand side response. Demand side response may not work for inertia response, but it can help in terms of achieving the primary and secondary frequency response. And other solution is CCGTs, which has been there already, but a lot of grids are actually procuring the CCGT service just for the spinning reserve. So they just always keep quiet, just running, and only available to provide the frequency response. And as they do not, well, they do participate in normal energy markets, but they never get a chance because they're expensive. But they will get a chance in the ancillary service as a frequency support. For example, in Germany, a lot of gas plants which are mothballed, means completely shut down previously because of not getting into the market, because they can't sell. There is a lot of renewable energy on the system, so they can't really sell the power from the expensive gas turbines. So what they are doing is that the grid operators are buying the services only for frequency support. So we are already there where the grids are seeing bottlenecks because of renewable energy sources. Then voltage and reactive power. So reactive power solution is again the converter design. So technically, there is no challenge, to be honest. The converters can be designed to provide as much as reactive power that the grid wants. But everything comes with a price. Converters are expensive as the size increases. As the capacity increases, they become much more expensive because the IGBTs have limited capabilities because of the thermal issues. So when you go to high voltage and high power levels, they become much more expensive than small rated IGBTs. It's not a proportional relation. It's almost kind of exponential relation. And other solutions is, you can say well-known SVCs or STATCOMs. And you will see that in real world, a lot of wind farms have already actually have either SVC or a STATCOM as a solution to provide the reactive power support. Fault ride through, again, the converters can provide the required amount of reactive current if they are designed to do so. That again requires the design margins to be chosen appropriately. So they should be designed much more than what they need to be doing for their primary purpose. So they are again expensive. Other solutions is STATCOM. So in terms of power quality, so Harmonics, we know, we all, whoever is an electrical engineer here, we have all studied the Harmonics, the active and passive filters. They are still the solutions. We do offer that we have offered in various projects. So we do have design filters due to the kind of costs involved in active filters. Most wind farm developers or PV developers go for passive filters, which are tuned for 1 or 2 frequencies. Then for voltage dips, so one of the issues that I have not explained you here is in terms of challenges. So energization, when you're energizing the wind farm or solar farm, they can create voltage dips on the grid. And there are strict regulations by grid operators to what level they can go in terms of voltage dip. So because these wind farms have a lot of cables and the transformers, they do create a lot of voltage dip because they are energy sources. Some of the solutions we provide for these problems is point-on wave switching. So that is to choose on at what point on AC waveform the circuit breakers needs to be closed onto the grid to energize the system. So there is a lot of technical background on this. So if for example, if you're closing the breakers when the voltage is at 0, on that particular phase, you will see a lot of current drawn by the wind turbine, wind farms that will create voltage drop, huge voltage drops. But if you choose cleverly to close the breakers at a different point, somewhere close to the peak, the currents will be low and hence the voltage dip will be low. But it doesn't work all the time because it requires a lot of sophisticated measurement system and a very quick acting circuit breakers and all that. So other solutions we do provide is pre-insertion resistors. So when they energize the wind farms, during the energization, these resistors come into picture in series to the system and absorb the energy instead of impacting on the grid. So I'm not going into that detail because it's a bit of too technical to explain. So I just limit to myself on the harmonics side. Okay. Yes. So some real world examples I said. Let me go through these. So first example I'll talk about is the inertia challenge. So as I explained you earlier, because of the renewable energy sources, the grids are becoming more, the frequency is becoming more volatile. The frequency excursions are becoming more volatile. So last year, a small isolated power system operator, which please do remember that I cannot disclose some of the information which is pretty confidential. So I will try to say, when I say South American country, I cannot tell you which country it is because it becomes too political, you know, because of the confidentiality issues. So in that country, there is a small area which the power grid is running on its own. The reason is that because of the hard terrain to cross the overhead lines or under no chance of underground cables, but overhead lines, they have always been running their system on their own. So with the present peak demand is around 350 megawatts. It's not a small microgrid or anything like that. It's a big system, considerable system, but it's not connected to the national grid. So they came up with a problem saying that at the moment they have around 30 megawatts of PV in the system. And on some days when the PV is running at full capacity and the demand is quite low, so all the conventional plants, like they mostly run on gas turbines and diesel generators. So they take out those and run the system mainly on these PV plants. And there are two plants, two 15 megawatt PV plants, and are remaining on gas turbines. So they are already seeing huge frequency excursions even during cloud passage. So when the cloud covers the PV farms, so I'm showing you here one example below. In this picture, the red one is the frequency of the system and the blue one is the output power of the PV plants. So there was a cloud passage and the output power is dipped by around just about 8. It's about 62 around around 50 megawatts. Sorry, no, from around 30 to 15, around 15 megawatts. So nearly 50% drop in the output power. That created a frequency drop almost up to 59.5 hertz, which is approaching the under frequency load shedding. So what these grid operators do is that they don't actually wait for the system to reach even the settings. They always watching it. Sorry, anybody wants to say anything?
No, sir. No, sir.
All right, okay. Yeah, if you can stop me. Maybe I should have told you. You can stop me if you want to ask me a question, but I will open up the floor afterwards anyway. So, so under frequency load shedding, so they don't even wait for the frequency to fall to the settings. There will be some manual intervention already, and they are already disconnecting the huge loads. So they came to us asking what can be done. And they are already aiming for 40% of renewable energy penetration levels by 2030. I told you that this system particularly, the generators are running on diesel, and which is pretty expensive for them. So they are migrating to renewables. So then they know that with 40%, they cannot manage the grid. So they came to us asking what can be done. So what we have provided, so anyway, so I already talked about that. So we studied various solutions, including interconnections with grid, international, the national grid, and other forms of solutions. But we came up with a solution to use battery energy storage that can, which basically interface to the grid with power electronic system. So the battery energy storage system can respond almost instantly to the frequency changes. So the problem is inertia. The grid is, they want the instant within 1 second response. So after simulations, we found out that, so how do we, how did we approach? So we call this as a synthetic inertia. So what it does is the battery energy storage systems, they keep it almost just for spinning purpose. So they are usually fully charged and only kept for the frequency response service. So as soon as the frequency starts falling up, the BESS, battery energy storage system, starts injecting or discharging or charging. And it happens within 1 second. So this we call it as synthetic inertia, because this is not coming from a rotating part, rather it's coming from a energy storage system, which is a kind of a static energy. So we call it synthetic energy, inertia. So the response after an extensive simulations, considering all the worst case scenarios, like the scenarios is like, so one of the worst case scenario is what happens when there is already cloud cover on a PV farm, and at the same time, one of the gas turbines trips. That is the worst case that the grid can see, which is they have to secure against. It can happen in any other cases, but in terms of N-1 security or N-2 security, that is the worst case the grid operator needs to maintain. So we did a lot of simulations in PSSE, and we found that in the current scenario, they need around 40 megawatts battery output and should be sustained for 30 minutes. That's also to provide primary and secondary frequency response. And going forward in 2030 scenario, where they want 40% renewables, they can manage with a 70 megawatt, 30-minute battery energy storage. So this is how we approach to, so there is a lot of technical challenges here. We have to consider every potential scenario, and there will be a lot of assumptions, there will be approximations, but in the end, we have to prove them that by doing worst case energy system simulations, we have to show them that grid can cope or integrate the required renewable energy with this solution. All right, so next example I'm going to give you is the one I worked again, is the reactive power related one. So this is a 50 megawatt wind farm in a Central Asian country. So there, the wind farm was already designed, and they were taking up the, they were starting the development. The design was over. They were just starting the development. They have already purchased the wind turbines. I mean, they given already order for the wind turbines. But when they went to the grid operator, what the grid operator told is that you need to come up, well, you need to show that the grid, the 50 megawatt wind farm is compliant to all the grid code requirements. So they came to us asking to study all this. So one of the issues we found is that with the current design, the wind farm cannot meet the reactive power requirement. So here, left side picture shows the the wind farm layout. I just put it just to help you how the layout looks like in software. This is a power factory, Dixieland power factory. So it's made up of 13 turbines, each 3.9 megawatt. So what the grid operators usually look at is here at the connection point, sorry. At the connection point, they want the required reactive power to be supported by the wind farms. Now, so what are the requirements? On the right side picture shows the wind requirement, the blue square. I hope, sorry. Yeah, this blue square box shows the requirement. Just give me a minute. So let me go back again. So the blue block, square box, not exactly square box, it's a rectangle box, shows the reactive power requirement. On the y-axis, we have the voltage at the point of connection. And the x-axis, we have the reactive power lag or lead. Similar to what I had shown you earlier. So what was happening is that with the current design, it was unable to meet the requirement. So this was the lagging part. On the leading side, there was a shortage of nearly 12 MVAR. So for this, how do we do? We consider all the scenarios and do the load flow simulations and measure the reactive power export at the point of connection and plot that against the requirement, and we will find out what is the gap. So that gap has to be filled with some other form of support. So for that, what we proposed is a 12 MVAR STATCOM to be installed at the connection point, so just in parallel to the wind farm. And it can now make the reactive power support fully compliant. So you can see that the entire capability is either within or exceeding the requirement. So that is one example I wanted to show you. So this is purely through load flow, whereas in the previous example here, it was full dynamic studies in terms of frequency response. Given the time, sorry, I did not go through the full details, but I can share the slides. You can look at closely what is these graphs are showing. Okay, then fault ride through in the same wind farm, the 50 megawatt one. So the fault ride through requirement is basically in this particular grid, it's very very demanding. So they need the grid wind farm to be continue to operational when the voltage at the connection point is 0 for nearly 650 milliseconds. I think 650 milliseconds is correct. That's a very demanding requirement for the grid. And we found that the wind farm is marginally stable. You can see the oscillations. So this picture basically shows, the top picture shows the voltage dipping to 0 for 650 milliseconds, whereas the bottom picture shows the blue one is the real power output, red one is the reactive power output. And after the disturbance, machine is coming back to its original state. So blue one is coming back to blue again, red is coming back to red. But you will see that in the real power, there are a lot of oscillations. So the plant was actually marginally stable, but it was failing the one of the criteria, which is the power should not have oscillations beyond a few cycles. So in this case, what happened is that because they have already purchased the turbines and the design was nearly execution stage, so they have so they sought a exemption from the grid operator for this particular aspect. So, I mean, this is the worst case scenario when the grid is at its lowest fault level, that's very weak, and it's happening maybe once in a lifetime. But the grid still require that to be satisfied. So they could get away with that. They got an exemption and they did not do any technical solution in this case. But otherwise, what we would do is we will actually tell them to install either a supporting battery energy storage system. No, sorry, either a support to STATCOM, additional STATCOM, or go back and purchase different turbines. All right, so that's what the presentation covers. So I hope I covered all the important challenges and some of the practical solutions that I've been involved in. And hopefully it was interesting and helpful to you. So if you have
Yes.
any questions, please do ask me. We don't, yeah, I'm happy to answer. Thank you.
Yes, sir. It is very interesting and informative also. One question was from a participant name.
Sure.
From solar system, what are the drawbacks in series and parallel PV array configuration during partial shading conditions?
Well, okay. So to be honest, I'm not a I'm not a renewable energy engineer, but rather a power engineer. But I will try to answer. So in terms of for partial shading, series and parallel, so the drawbacks is, well, you would, if it is the series systems, you are looking for the voltage buildup, or whereas if it is a parallel system, you're looking for a current buildup. So for a partial shadow, you will end up not having any energy from some of the panels, and you will lose the, for example, if it is series one, you will lose the potential to build the required voltage and hence to store the, well, hence to supply to the grid. Now, usually what happens is that the PV farms are designed to take up a certain level of partial blockage in terms of, I mean, even they are designed to a loss of some of the cells. So it depends on how extensive is the blockage. But in terms being a power engineer, I can only tell about what can happen in terms of build up the voltage and currents. But in terms of actual mechanics of exporting the panel out, the conversion, I'm not good at that.
Thank you, sir. Thank you for your information.
Okay, no worries.
Now, thank you for your informative information given to us, all the participants. Now I request our HOD sir, Dr. P. Ramesh Garu, to give you a vote of thanks.
Hello. Uh, Thank you, sir. You have given the wonderful and also useful information to all the participants. I hope all the participants have received the real challenges and also solutions happening in the real-time scenario. Really, I hope this is very useful for especially researchers who are really working on the renewable energy sources and also power system area. Definitely, we have created the good opportunity for them to know about the real-time situations happening in the market. Thank you, sir. Thank you very much for your acceptance, as well as you have spent almost all 1.5 hours. I know your time value, but even though at the busy moment also you have accepted our proposal and also you given good information to our participants. Thank you, sir. Thank you very much. And
No, thank you for giving me the opportunity. I hope it's not too technical, so hopefully you can digest a bit. So yeah, thank you.
yes, sir. Yes, sir. Yes, sir. Yes, sir. Thank you all the participants, and also I congratulate to our coordinators of this webinar, Srivani and Srikant Maheshwar Reddy has done good work for this webinar, and also all the best for all the participants for the future webinars. Thank you. Thank you very much.
Thank you all. Take
Thank
care.
you, sir.
Thank you all. Take care. Bye-bye.
Thank you. Thank you, sir.
Right. Yep.
Help. Now, Assistant Professor K. Swati will give you a vote of thanks for all the participants.
A very good and warm afternoon to everyone. I, K. Swati, Assistant Professor, EEE Department, Nalla Narasimha Reddy Educational Society Group of Institutions. I want to express my thank out loud to today's speakers, Dr. Nagaraj Pogak Garu, for his visionary words on grid connection of renewable energy generation challenges and solutions. I thank all the participants from various institutions. Thank you one and all. I thank all our management for giving permission for conducting this national webinar. I express my thanks to our HOD, Dr. B. Ramesh Garu, all the faculty and staff who supported this webinar directly or indirectly. Thank you, sir, for your efforts for the webinar. The webinar is very effective and we are very happy to listen to your words, sir. Thank you once again and one and all.
Thank you, Swati ma'am. Now I request all the participants to fill the feedback form and the certificate will be received soon. Thank you one and all. Within 2 days, your certificates will be received. Shrikant sir.
Hello, madam.
Sir, you can end the meeting, sir.
Madam, somebody not still yet filled the feedback form. I wait for 2 to 3
Okay,
minutes. madam.
okay. We'll be leaving the meeting, sir.
Okay, okay, right, madam.
Thank you, sir.
If all the participants have filled out the feedback form, you can exit from the Zoom meeting.